Welcome to EDU World Space.
Okay, so for this problem, what we want to find is the filter through which Vega would appear the brightest. And in order to do that, we are going to need to look at the ratio of radiant fluxes received through each filter. Whenever I have these problems, I always want to start by writing what I know. So let's go ahead and start out with the U filter. Well, for the U filter, I have a central wavelength, lambda U, equal to 365 nanometers. I also have a bandwidth of the U filter, delta lambda U, equal to 68 nanometers. For the B filter, I have a central wavelength, lambda B, equal to 440 nanometers, and a bandwidth, delta lambda B, equal to 98 nanometers. And for the V filter, I have a central wavelength of lambda V equal to 550 nanometers, and a bandwidth, delta lambda V, equal to 89 nanometers. Now, here's the trick. You have to assume that S equals 1 inside the filter, bandwidth, and S equals 0 everywhere else. Okay, so using this information right here, we need to look at the ratio of the radiant fluxes. In other words, we need to look for the following three ratios. Here's ratio number 1. Integral 0 to infinity, f of lambda, s of u, d lambda, divided by integral 0 to infinity, f of lambda, s of b, d lambda. I need to look at the ratio number 2 of the integral 0 to infinity, f of lambda, s of u, d lambda, over integral 0 to infinity, f of lambda, s of v, d lambda. And the third ratio to be integral 0 to infinity, f of lambda, s of b, d lambda, over integral 0 to infinity, f of lambda, s of v, d lambda. All right, so these are the three ratios that we need to find, and we want to remember that there is an approximation that we can do. For monochromatic flux at least. So when we have that monochromatic flux, we can approximate this first integral to be lambda b over lambda u to the 5th power multiplied by e to the hc over lambda b kt minus 1 over e to the hc over lambda u kt minus 1 multiplied by delta lambda u over delta lambda b. So let's do a similar approximation for the second and third ratio. Okay, here we go. Okay, so we would get lambda v over lambda u times e to the hc divided by lambda v kt minus 1 over e to the HC over lambda U KT minus 1 multiplied by delta lambda U over delta lambda V. And then finally, for our third one, we get an approximation equal to lambda V over lambda B multiplied by E to the HC over lambda V KT minus 1 over E to the HC divided by lambda B KT minus 1 multiplied by delta lambda B over delta lambda V. Okay, so these are our three ratios and their approximations. Here we go. Now, all that you have to do is plug in the values for a temperature of 9600 Kelvin. T goes 9600. You plug that in right there. We know the values of lambda B. We know the values of lambda U. We know the value of lambda V. We also know the value of delta lambda U. We know the value of delta lambda B. And the value of delta lambda V. They're all right up here. Now, what is this H and what is C? Remember that H equals Planck's constant. C equals the speed of light. And K equals Boltzmann's constant. So these are just very long values. H is like 6.626 times 10 to the negative 34. C is 3.0 times 10 to the 8th. And then K is like 1.38 times 10 to the negative 20 something. All that you have to do is plug these values in to your calculator. You just look them up either through your book or on Google, plug them in, and you get a value approximately for this first one equal to 0.862. For the second one, I get 1.42, and for the third one, I get 1.64. So, what does that mean? It means, look at these values. It means that Vega would appear the brightest when appeared through which one? Well, 1.64 compared to 1.42 compared to this guy. That means the B filter would appear brightest through the B filter. And what do you think would be the faintest? Well, the faintest would have to be this guy up here. So the V filter. All right, and that's it.